Hi, and welcome to AP Physics C, Mechanics. In this lecture, we're starting work, which means energy transferred by a force as something moves. The big idea is simple but powerful. Forces do not just change motion, they can move energy into or out of a system. Next, we'll map out how this idea connects to dot products, kinetic energy, and real physical situations. This roadmap shows the path we will take from the basic meaning of work to the full AP Physics C toolkit for calculating it. The core idea is that work is energy transferred by a force as an object moves through a displacement. If there is no displacement in the direction of the force, that force does not transfer energy by work. Mathematically, work equals force dot displacement, which also equals force times displacement times cosine of the angle between them. The dot product is what tells us whether the work is positive, negative, or zero. For a constant force, the dot product is enough. For a variable force, we add up many tiny contributions, and on a graph of parallel force versus displacement, that total work is the area under the curve. This integral says work equals the accumulated parallel component of force over the displacement interval. In words, we are summing force along the direction of motion from the initial position to the final position. A major payoff is the work energy theorem. Net work equals the change in kinetic energy. So if the total work on an object is positive, its kinetic energy increases. If the total work is negative, its kinetic energy decreases. Finally, we will compare conservative and non-conservative forces. Conservative forces depend only on endpoints, while non-conservative forces can depend on the path and often dissipate mechanical energy, like friction turning motion into thermal energy. Next, we will sharpen the vector language behind that dot product, because direction is what makes work more than just force times distance. Before we define work mathematically, we need one vector tool and one energy idea. The main twist is that work is a scalar, even though the force causing it and the displacement it acts through are vectors. A scalar is just a number with units, not a direction. So when a force vector and a displacement vector combine to make work, something has to turn those directions into one signed number. That tool is the dot product. A dot B equals the magnitude of A times the magnitude of B times the cosine of theta, where theta is the angle between the two vectors. The picture is showing why the angle matters. Only the part of the force pointing along the displacement lines up with the motion. The perpendicular part does not push energy into or out of the motion along that path. So the key idea is this. Only the parallel component of force transfers energy through work. If the force points with the displacement, work is positive. Against it, work is negative. Perpendicular to it, the work is zero. Now connect that to kinetic energy. Kinetic energy equals 1/2 times mass times speed squared, so speed matters a lot because it is squared. That means changing an object's speed means changing its kinetic energy. In the next step, we will use work to describe exactly how forces create that energy change. Work is the physics word for energy transferred by a force as something moves. The important idea is that the force has to act along the path of the point where the force is applied. Mathematically, work from point A to point B equals the integral of force as a function of position dotted with dr. That means we add up tiny dot products between the force and each tiny displacement along the path. For the common case of a constant force, work equals the parallel component of the force times the distance. Using the dot product, that is also force times distance times cosine theta, where theta is the angle between the force and the displacement. Look at the package moving to the right. A horizontal push can transfer energy into the package, but a vertical force like the normal force or weight does not transfer energy through this horizontal displacement. The sign of work tells you the direction of energy transfer. A force component along the displacement does positive work, opposite the displacement does negative work, and perpendicular forces do zero work. If there is no displacement, the work is also zero. The SI unit of work is the joule. 1 joule is 1 Newton meter, because work is force times displacement. For the package displaced to the right, which work signs are correct? Choose the option that matches the applied force, friction, the normal force, and weight. A is correct. The applied force has a component along the displacement, so its work is positive. Friction is opposite the displacement, so its work is negative. The normal force and weight are perpendicular to the horizontal displacement, so they do zero work. The tempting mistake is treating vertical forces as doing work just because they act on the package. Perpendicular forces transfer no energy through work. Keep that angle idea in mind. Next, you will get to change the force direction and watch the work change in real time. Start with the angle at 0 degrees. The force and displacement point the same way, so the dot product is positive, and with force and distance fixed, this gives the largest possible work. Now set the angle to 90 degrees. The force is still there, but none of it points along the displacement, so the parallel component is 0, and the work is 0. Finally, move past 90 degrees to 150 degrees. The parallel part of the force now points opposite the displacement, so the dot product becomes negative, and the force removes energy through negative work. Try changing the angle yourself, and watch the sign switch as you cross 90 degrees. Let's pause to check how work depends on direction. Focus on the component of force parallel to the displacement. A student pushes a box to the right, and the box moves to the right across the floor. What is the sign of the work done by the student's push on the box? The push and displacement point in the same direction, so the angle between them is 0 circumflex circ, and W equals sign FD cos theta is positive. The tempting mistake is to think mass is needed, but mass is not needed to decide the sign of work from force and displacement directions. A constant force of 40 newtons pulls a sled 3.0 meters at an angle of 60 degrees above the horizontal. The sled's displacement is horizontal. What is the work done by the pulling force? Use the component of the force parallel to the displacement. W equals sign FD cos theta equals sign 40 text N3.0 text M cos 60 circumflex circ equals sign 60 text J. The tempting answer 120 text J comes from using the full force without the cosine factor, but only the parallel component does work. A block slides horizontally across a level table. The table's normal force points upward while the block's displacement is horizontal. Which statement correctly describes the work done by the normal force? The normal force is perpendicular to the horizontal displacement, so theta equals sign 90 circumflex circ and W equals sign FD cos 90 circumflex circ equals sign 0. The tempting idea that the normal force does positive work because it supports the block is incorrect. Supporting the block does not transfer energy through horizontal displacement. Now we combine all the individual work contributions into one result. Instead of asking what one force does, we ask what all the forces together do to the object's motion. Net work means the total work done by all forces. So, net work equals the sum of each individual work contribution, including positive, negative, and zero work. Because work is a scalar, these contributions add algebraically. That means positive work increases the total, negative work subtracts from it, and zero work does not change it. The work energy theorem says that the change in kinetic energy equals the net work. In plain language, the total work done on an object tells you how its kinetic energy changes. For our object model, we are treating the object like its relevant points move together with the center of mass. In that case, the work we calculate changes only the object's kinetic energy, not internal energy or rotation. Think about the package example. The applied force does positive work because it points along the displacement, while friction does negative work because it points opposite the displacement. The normal force and the weight do zero work here because they are perpendicular to the package's horizontal displacement. They matter for the force picture, but they do not directly change the package's translational kinetic energy through work. So the big takeaway is this. Add all the work terms first, then connect that net work to the change in kinetic energy. Next, we will extend this idea to forces that are not constant. When the force is not constant, we cannot just multiply one force value by the whole displacement. Instead, we chop the motion into tiny pieces and add the tiny bits of work. The tiny amount of work, called dW, equals the force vector dot the tiny displacement vector, dr. The dot product means only the part of the force pointing along the motion transfers energy. In one dimension, that becomes work equals the integral from the initial position to the final position of the parallel component of force as a function of x times dx. For AP Physics C, this integral form is the main definition of work when the force changes with position. On the graph, look at force along the path on the vertical axis and displacement on the horizontal axis. Each thin strip has area force times a tiny displacement, so adding all the strips gives the total work. That area is signed area. Area above the axis is positive work. Area below the axis is negative work, because the force component is opposite the displacement there. Try this concept check. If the parallel force is 3x newtons from x equals 0 meters to x equals 2 meters, what is the work? Think area under the changing force graph, not just the final force times distance. Correct. W int underscore 0 squared 3x, dx equals sign 6 text j. The tempting 12 text j uses only the final force times displacement, not the area under the changing force graph. So the big takeaway is that variable force work is an accumulation. Tiny dot products along the path, or in one dimension, signed area under the force versus position curve. Next, we will use this work idea to sort out a special kind of force. Some forces have a special shortcut built in. For a conservative force, the work can be found from just the starting and ending configurations, without tracking every tiny part of the route. A conservative force means the work depends only on the endpoints. Gravity and ideal spring forces are the classic examples you will see often in AP Physics C. Look at the different paths between the same starting and ending configurations. Even if one path curves and another is more direct, the gravitational work is the same because only the change in height matters. This is why potential energy is linked only to conservative forces. A potential energy function can describe the energy stored by position or configuration, but that works only when the path does not affect the work. The equation says, work done by a conservative force equals negative the change in potential energy. Here, change in potential energy means final potential energy minus initial potential energy. That negative sign is important. If the conservative force does positive work, the associated potential energy decreases. If it does negative work, the potential energy increases. For a closed path, the system comes back to its initial configuration. That makes the change in potential energy zero, so the net work done by that conservative force over the whole loop is also zero. So the big test is path independence. Same endpoints, same work. Next, we will contrast this with forces where the route absolutely does matter. A non-conservative force is different because the route matters. If you take a longer path, that force can do a different amount of work, even if the start and end points are the same. The big AP examples are friction and air resistance. Both depend on the actual motion through the environment, not just the initial and final positions. Look at the rough paths in the picture. The longer the object scrapes along the surface, the more mechanical energy gets transformed into thermal energy and sound. For kinetic friction, we often model the dissipated energy as the kinetic friction force times the path length. Here, dissipated energy means mechanical energy that has been spread out into less useful forms, mostly heat and sound. Be careful with the sign. Friction usually points opposite the motion, so friction does negative work on the moving object. So the pattern to remember is this. Conservative forces care about endpoints, while non-conservative forces care about the path. Next, you'll check that distinction in a few quick questions. Pause here to check your understanding of conservative and non-conservative work. Focus on whether the work depends on the path and how that connects to potential energy. Which statement best describes the work done by a conservative force between 2 points? For a conservative force, work is path independent. It depends only on the initial and final positions. A tempting misconception is that conservative work is always positive, but the sign can be positive, negative, or zero, depending on the motion and force direction. An object moves from the same starting height to the same ending height along 2 different paths near Earth. Which statement correctly compares the work done by gravity on the 2 paths? Gravity is conservative, so its work depends only on the change in height, not the shape or length of the path. The tempting error is to choose the longer path, but path length does not determine gravitational work. A conservative force acts on an object as it moves around a closed path and returns to its starting point. What is the total work done by that conservative force over the full path? For any conservative force, the work done over a closed path is zero because the initial and final positions are the same. The tempting distance-based answer is wrong because conservative work depends on endpoints, not total distance traveled. Which pair of forces is best classified as non-conservative in the situations usually considered in mechanics? Friction and air resistance are standard non-conservative forces. Their work depends on the path and often dissipates mechanical energy into thermal energy. Gravity is a tempting distractor because it can change kinetic energy, but it is conservative and can be associated with gravitational potential energy. Here is a compact strategy for work problems. Decide what energy model you are using before you write equations. That one choice keeps you from double counting energy or mixing incompatible ideas. First, define the model. Choose the system: the object alone, the object and earth, or the object and spring. A system is the set of things you are treating as one unit, and that choice decides which interactions are internal. If gravity or a spring interaction is inside the system, its energy can be stored as potential energy. If that interaction is outside the system, then the force does work on your system instead. Next, audit the forces. List every force on the object, then mark whether each force does positive work, negative work, or zero work. Positive work adds kinetic energy, negative work removes kinetic energy, and zero work means the force has no component along the displacement. For a constant force, work equals force times displacement times cosine of theta. Here, theta is the angle between the force and the displacement, so this formula really means use only the part of the force along the motion. For a variable force, use the integral of the parallel force with respect to position. In words, you add up tiny pieces of work as the force changes along the path. If you are using the object model, the change in kinetic energy equals the sum of all the work done on the object. Use potential energy only for conservative interactions included inside the system, not for forces you already counted as external work. Finally, handle friction and air resistance carefully. They are path-dependent dissipative forces, so account for the mechanical energy loss separately. Keep this checklist in mind, because next we will organize the key terms and formulas you need most often. Use this page like a compact reference sheet. It collects the formulas and vocabulary you need when you decide which work model fits a problem. The general definition of work is the integral of force.dr, meaning you add up the force component along each tiny displacement. For a constant force, work equals the parallel component of force times displacement, or force times distance times cosine theta. The dot product of A and B equals a B cosine theta. That angle factor is why work is a scalar, not a vector, even though force and displacement are vectors. A scalar can be positive, negative, or zero here, depending on direction. A force helping the motion does positive work, a force opposing it does negative work, and a perpendicular force does zero work. The work-energy theorem says the change in kinetic energy equals the net work, which is the sum of the work done by all forces. This is your main bridge from forces to speed changes. For a conservative force, the work equals negative change in potential energy. Conservative also means the work around any closed path is zero, so only the starting and ending positions matter. Non-conservative work is path-dependent. Friction and air resistance are the common examples, and they often dissipate mechanical energy into thermal energy or sound. Keep these distinctions sharp: constant versus variable force, net work versus individual work, and conservative versus non-conservative. Next, you will use them in a quick final check. You're almost done. Use these questions to check whether you can choose the right work model, read work from a graph, and connect net work to energy changes. A constant force of magnitude F acts on a box, while the box moves through a displacement delta x at an angle theta relative to the force. Which expression gives the work done by that force? The work done by a constant force is W equals sine F delta x cos theta, which uses the force component parallel to the displacement. Choice A is tempting, but it is only valid when the force is exactly parallel to the displacement, so theta equals sine 0 circumflex circ. A force component parallel to the motion increases linearly from 0 newtons at 0 meters to 6 newtons at 4 meters. What is the work done from 0 to 4 meters? Work is the area under an F underscore parallel versus x graph. The graph forms a triangle, so W equals sine 2 frac 124 text M6 text N equals sine 12 text J. Choice D is tempting because it multiplies base times height, but that would be the area of a rectangle, not a triangle. An object has positive work done by an applied force and negative work done by friction. The applied force does 30 joules, and friction does negative 40 joules. What does the net work tell you about the change in kinetic energy? The net work is W underscore text net equals sine plus 30 text J, 40 text J equals sine minus 10 text J. By the work kinetic energy theorem, W underscore text net equals sine delta K, so delta K 0 and the object slows down. Choice C is tempting if you focus only on the applied force, but kinetic energy responds to the net work. A block slides down a rough ramp. Earth's gravity and kinetic friction both do work on the block. Which classification of these forces is correct? Gravity is conservative because the work it does depends only on the initial and final positions, not the path. Kinetic friction is non-conservative because its work depends on path length and dissipates mechanical energy. Choice D is tempting because friction is non-conservative, but gravity is still conservative in this context. After that final check, here are the big ideas to carry into AP-style work and energy problems. When you see a force and a displacement, immediately ask, what energy is being transferred, and by which component of the force? Work is energy transferred by a force through a displacement. In calculus language, work equals the integral of force dot dr, which means you add up tiny pieces of force along tiny pieces of motion. The dot product is the key filter here. Only the parallel component of the force contributes to work. A perpendicular force can bend or redirect the motion, like centripetal force in circular motion, but by itself, it does not change kinetic energy. The work energy theorem says that the change in kinetic energy equals the sum of all the work done. So if net work is positive, kinetic energy increases. If net work is negative, kinetic energy decreases. And if net work is zero, the speed may stay the same even if direction changes. For force types, separate conservative from non-conservative. Conservative work is path-independent and connects cleanly to potential energy, while non-conservative work is path-dependent and often dissipates mechanical energy, such as friction turning organized motion into thermal energy. Graphically, a force parallel to the motion versus displacement graph turns work into signed area. Area above the axis gives positive work, and area below the axis gives negative work. That is the core toolkit. Dot product for direction, network for kinetic energy change, force type for energy bookkeeping, and graph area for calculation. Keep those 4 moves organized, and work problems become much more manageable. Nice work finishing this lecture.